Okay, today we're going to look at some other trigonometric identities. I've written down a couple identities from our previous section. These were the sum identities. The sine of u plus v is sine u cosine v plus sine v cosine u. And remember, if I had sine of u minus v in the middle there, I would have a minus on the right-hand side too. And my cosine formula, cosine u plus v, is cosine u cosine v minus sine u sine v. Same thing, if I had cosine u minus v, then over on the right-hand side, I would have a plus in the middle. Turns out that those two identities help us to prove an awful lot of other identities. So let me give you a few of those. First group we're going to look at are called the cofunction identities. And I'm not going to write down all of these. I'm going to write down the three important ones. The three important ones are sine of pi over 2 minus x is cosine x, and cosine of pi over 2 minus x is sine x, and tangent of pi over 2 minus x is cotangent x. Now, these really shouldn't be a big surprise if you go back and think about what we learned a few sections ago in graphing. Basically, what we have here, sine of pi over 2 minus x, that's a translation of the sine graph. If you slide the sine graph left or right by pi over 2, you see that it lines up very well with the cosine graph. And that's really all that identity says. Now, the same with the next one. All right, well, let me just prove one of these real quickly. And you can see where these identities I wrote above are going to become important. Sine of pi over 2 minus x, according to that first formula, that would be sine of pi over 2 cosine x minus sine x cosine pi over 2. All right, but we got some of our special angles here. Sine of pi over 2. Sine of pi over 2 happens to be 1. So I have 1 times cosine x. That's cosine x. And on this one, cosine of pi over 2 happens to be 0. So the cosine pi over 2 sine x, that's 0. So we do get exactly cosine x. Okay, so those are just called the cofunction identities. Not used a whole lot, but they were important back in graphing. The next group of identities is called the double angle identity. All right, so this one has, for example, sine of 2x. Well, sine of 2x, I could think of that as being sine of x plus x, right? Because 2x is x plus x. Then I can use my sine rule. So that's going to be sine x cosine x plus sine x cosine x. So that's 2 sine x cosine x. All right, so the important thing to note here is that sine of 2x does not equal 2 sine x. You can't just pull the 2 out front. When you have sine of 2x, you get 2 sine x cosine x. Again, if you think of graphing, it should make a lot of sense to you that you cannot pull the 2 out front. Because the 2 here, the 2 on this left-hand side, that affects the period, where the 2 here, that affects the amplitude. So again, if you think of graphing, it should make a lot of sense to you that, hey, the 2 just doesn't come out front. All right, let's try it with cosine. Cosine of 2x, same trick, that's cosine of x plus x. All right, let's see, that would be cosine x minus sine x. So we could write that as cosine squared x minus sine squared x. All right, so that's one form that you will see of this identity. What do I mean by one form? What are others? Well, let me show you. The other forms come from this. I could write this as cosine squared x minus sine squared x is 1 minus cosine squared x. That's our Pythagorean identity. I run that minus sign through and combine my like terms. I get cosine squared x minus 1. Oops, I wrote plus 1. Minus 1. Or, here's another choice. I could write this, I had cosine squared x minus sine squared x. I could take that cosine squared x that was out front and write it as 1 minus sine squared x. And then I would still have the minus sine squared x from the original rule I had. So I get 1 minus 2 sine squared x. And you know what? I botched the one up above. I have a cosine squared x and another cosine squared x. That should be 2 cosine squared x. Okay, so there are 3 different forms of the cosine 2x identity. Cosine 2x can be written as cosine squared minus sine squared. It can be written as 2 cosine squared x minus 1, or it can be written as 1 minus 2 sine squared x. All right, I'm not going to prove this one for you, but you could grab the tangent of u plus v formula that we had in the last section and just plug in x plus x, and you would see that tangent of 2x turns out to be 2 tangent x over 1 minus tangent squared x. All right, so here's a couple of examples of using these identities. Let's say you're told cosine theta is 5/13 and theta is in quadrant 1. I want to know the value of sine 2 theta, cosine 2 theta, and tangent 2 theta. Well, let's see. What do I do? If I want to find sine of 2 theta, that's going to be 2 sine theta cosine theta. So in order to find the value of sine 2 theta, I need to know the value of sine theta and the value of cosine theta. I know the value of cosine theta. Cosine theta is 5/13, so I have to find sine theta. I think I can do that by drawing a little triangle here. So here's my angle theta. Cosine is 5/13, so that's adjacent hypotenuse. Go ahead and use the Pythagorean theorem. Let's see, you'd have 169, that's 13 squared. 5 squared is 25. 169 minus 25 happens to be 144. You'll find that that side has to be 12, which tells me sine theta is 12 over 13. All right, so I'm all set here. That's 2 times 12/13 times 5/13. So let's see, that's 169 on bottom. And on top, 12 times 5 is 60. 60 times 2 is 120. So you get 120 over 169. All right, to find cosine of 2 theta, I get to pick from any of the 3 forms I want. Now, if I'm doing this problem, I personally would use the 2 cosine squared theta minus 1 formula. And the reason I would use that formula is the cosine value, cosine of theta equals 5/13, was given to me. I could use the cosine squared minus sine squared, but then I have to use sine theta is 12/13, which I derived. And you might remember back when we were dealing with exponential functions and such, I told you it's always a good idea to not use derived information. It's always good to use exact values, given values if you can. So that's why I would do this one. So I would have this as 2 times 5/13 squared minus 1. So that's going to be 2 times 25 over 169 minus 1. That's 50 over 169 minus 1. Think of 1 as 169 over 169, and then 50 minus 169 should be minus 119 over 169. And now a good question is, does it make sense that that answer is negative? And yes, it does. If you recall that theta is in quadrant 1, so if I double theta, theta is between 0 and 90, if I double that angle, I'm going to get an angle that's most likely in quadrant 2. If the angle is between 45 and 90, then when I double that, I'm going to get something between 90 and 180. So it does make sense that the angle could be in quadrant 2. If the angle's in quadrant 2, cosine should be negative. All right, then to find tangent of 2 theta. Personally, I very rarely use the tangent 2 theta formula, the tangent 2x. I would simply take my sine of 2 theta, and I know that's something I derived, but if I use the tangent 2 theta formula, I'm going to have to use derived information anyway. Divide it by my cosine. We reduce our fraction, we get negative 120 over 119. All right, our next set of identities are called the half-angle identities. And these are really a special case of the double-angle identities, which are really a special case of the sum and difference identities. All right, so here's the idea with this one. We have, which one do I want to do first? I guess it doesn't matter. Cosine of 2x is 1 minus 2 sine squared x. I'm just going to rewrite this identity. I'm going to move the 1 over. So I'm going to write this as minus 1 plus cosine 2x minus 2 sine equals minus 2 sine squared x. And then I'm going to divide by minus 2, so I get 1/2 minus 1/2 cosine 2x is sine squared x, and that's usually written as 1 minus cosine 2x over 2 equals sine squared x. And actually, this one has a name. This is called power reduction identity. Your book doesn't call it that. But we do use that one in calculus a lot, so that's an important one. Basically what it allows you to do is get rid of the square, sine squared x. You can write it as 1 minus cosine 2x over 2. But what we're going to do is we're going to use the half-angle identity. So we're now going to replace x with u over 2 and square root both sides. So I get plus or minus the square root of 1 minus cosine of u, because when I put a u over 2 in there, the 2's cancel out, divided by 2 equals sine, because I did the square root of u over 2. So that's known as the half-angle identity for sine. Sine of u over 2 is plus or minus 1 minus cosine u over 2. And you can do the exact same thing with the cosine formula. You start with cosine 2x is 2 cosine squared x minus 1. And you'll find that cosine of u over 2 is plus or minus the square root of 1 plus cosine 2x. 1 plus cosine x, I mean, over 2. And then you can work it out. Again, this is shown in your book. I'm just going to write this down. Tangent of x over 2 can be written a couple different ways. It can be written as sine x over 1 plus cosine x. And it can also be written as 1 minus cosine x over sine x. Okay, so there's a couple identities for that. Okay, the big question students usually have here for me is, how do I know if I should use the plus or the minus on the square root? And my answer to that is it all depends on your angle. What do I mean by that? What if I asked you to find the cosine of 75 degrees? Well, cosine of 75. 75 is not one of the special angles that shows up on our list in our table. But it turns out that 75 degrees is the same as 150 degrees over 2. And 150 degrees, while not on our table, is an important angle. And what I mean by that is 150 degrees is over here in quadrant 2. It has a reference angle right here of 30 degrees. So we can find the cosine, sine, and tangent of 150 degrees by using our reference angle information for 30 degrees. All right, so this is going to be plus or minus the square root of 1 plus cosine x over 2. Do we use plus or minus? The answer is, look at our original angle. Our original angle is 75 degrees. 75 degrees is in quadrant number 1. In quadrant number 1, cosine is positive. If our original angle was in quadrant number 2, cosine would be negative, so then we would use the negative square root. That's how you tell. Look at your original angle. Our original angle is in quadrant 1, so we want the positive square root. So this is going to be the square root of 1 plus cosine of 150 degrees over 2. So that's going to be the square root of 1 plus. All right, now we got to do a little thinking here. 150 degrees has a reference angle of 30 degrees. Cosine of 30 degrees, I look back in my table, I get square root of 3 over 2. However, I'm dealing with 150 degrees, which is in quadrant 2, so I should have negative square root of 3 over 2. And then the whole thing is divided by 2. Okay, as far as I'm concerned, that's a perfectly acceptable answer. But if you're doing problems on the computer or looking up answers in the back of your book, it's not going to be written that way. What they're going to do is they're going to take 1 here and they're going to think of it as 2 over 2. So this would be written as the square root of 2 minus the square root of 3 over 2, all over 2. And then they take this 2 and they think of it as 2 over 1 and they flip and multiply. So in the back of your book, on the computer, the way the answer would be written is 2 minus the square root of 3 all over 4.